This is 6-4. Okay. Logarithmic functions. So we just kind of talked about where logarithmic functions come from. Now let's talk about the details. We've done this with every function we've dealt with so far. We've talked about the details of quadratic functions. We've talked about the details of polynomial functions. We've talked about the details of rational functions. Now let's do logarithmic functions. Okay, the domain is x is greater than 0. We just barely talked about that. That's because there's a vertical asymptote at 0. So our graph looks like that, right? The range, what's the range of a logarithmic function? All real numbers. Bottom to top. This keeps going up. Okay, what is the x-intercept of our function?
1.
The x-intercept of the function is always at 1 unless the graph has been transformed and moved around somewhere. So the x-intercept will always be 1, 0. In other words, anytime you plug 1 into any logarithm, regardless of the base, the answer is 0. Always. The log of 1 is always 0. Okay, y-intercept. None, because there is an asymptote. Where's the asymptote? X equals 0. Yes. Okay, now can we transform logarithmic graphs just like we can transform any other function?
Yes.
Yes, we can. What does each number do? A stretches and reflects. What does H do? Moves it left or right, the opposite direction. What does K do? Up or down, right? Do you want me to do any examples of that, or can you work through that on your own? Just the same old transformations we've been doing with every function, right? Experiment with it. I might try and create some videos to help you with it. Okay. Now we need to look at special bases. This is going away, I'm sorry. Special bases. We have two different special logarithms. One is called the common logarithm. The common logarithm is base 10. And it is the one on your calculator that just says log and has no base written. Don't need to write the number. So anytime you see a logarithm without the number written right there, it's base 10. If there's a number written there, then it's whatever base the number is. It can be decimals even. A base can be a weird number. Okay, in fact, this next one is a little weird. The other special base is called the natural logarithm. The natural logarithm, we will learn more about its essentialness when we get to sections 6 and 7 and 8. Okay, but it is base E. And if you watched my video for section 6.3 notes, you would know that E is a naturally occurring number that is in your calculator, and it's approximately 2.71. We will learn more about where that comes from in section 6. Okay, so instead of writing log base E for natural log, because we're going to use it so often, we just abbreviate it with an ln. Natural log x, but instead of being NL for natural log, it's ln written backwards. I have no idea who decided that, but that's the way it is. Okay. So ln x just means log base E. Okay? But we write it this way instead of this way. Get in the habit of doing that. Alrighty. Let's do some simplification problems really fast. So here's some examples. Find the exact value of log base 2 of 16. Now remember, a logarithm is an exponent. So the answer you're looking for here is an exponent. So what I like to do when I'm doing logarithms like this is I ask myself a question. Here's the question I would ask myself. Yes, because there's two of me, remember? So, 2 to what power is 16? Because remember, a logarithm is an exponent. So the question is, what's the power? 2 to what power is 16? So the answer in this case, the value of the function would be 4. Because 2 to the 4th power equals 16. I guess I should have put it in the blank. I don't know why I didn't. Okay, try another one. Here's a trickier one. Log base 3 of 1 over 27. What question do you ask yourself? 3 to what power is 1 over 27? Someone just said it's a negative, isn't it? Very good. What's the answer? The answer is in fact negative 3. Because 3 to the negative 3rd power means 1 over 3 to the 3rd power. And 3 times 3 is 9 times 3 is 27. Okay? Alright, I'm just going to leave that there. Now let's find some domains. Okay. Let's say our function log base 2 of x plus 3. We want to find the domain. What did we say earlier that we cannot plug into a function? Cannot be 0 or negative. So instead of thinking of what it can't be, what can it be? So x plus 3 must be greater than 0, right? What does that mean that x is going to be? X is greater than negative 3. There's your domain. Or another way to write that is negative 3 to infinity. Okay, let's try another one. G of x equals log base 5, 1 plus x over 1 minus x. So again, this stuff cannot be 0 or negative. So what do we do? Okay, what did I do on this other problem here? What did I do to solve this? I took the stuff and I set it greater than 0 and I solved it, right? So let's take the stuff, 1 plus x over 1 minus x, greater than 0, and solve it. It might look simple, it's not. This is a 5.4 inequality problem. What are the critical values? 1 is in fact a critical value because that would make the denominator 0. What else? Negative 1 is a critical value because that's an x-intercept. So we break it into negative infinity to negative 1, negative 1 to 1, 1 to infinity. We test our intervals. We plug it in, so negative 2. 1 plus a negative 2 is a negative. 1 minus a negative 2 is a positive. What's a negative divided by a positive? It's a negative. That one fails. Plug in 0. 1 plus 0 is 1. 1 minus 0 is also 1. That is positive. That one is good because it's greater than 0. Plug in a 2. 1 plus 2 is 3. 1 minus 2 is a negative 1. That's a negative. That's a fail. So what is the domain? The domain is simply negative 1 to 1, and that is it. Wasn't that fun? Alright, that's of section 4, unless you want me to do some examples. Oh, no, it's not.